Hello everyone, welcome to Soil Mechanics online course. Today we are going to study the Terzaghi's bearing capacity theory. Generally, we have three methods that can determine the ultimate bearing capacity of soil. They are in-situ plate load test, theoretical methods, and empirical methods adopted in different specifications. For plate load test, we will simply go through it, and for empirical methods, one can refer to different kinds of specifications for details. In this lecture, we will focus on the theoretical methods, and we will explain the Terzaghi's bearing capacity theory in detail. Plate load test is a field test for determining the ultimate bearing capacity of soil and the likely settlement under a given load. The plate load test basically consists of loading a steel plate placed at the foundation level and recording the settlements corresponding to each load increment. The test load is gradually increased till the plate starts to sink at a rapid rate. The total value of load on the plate in such a stage divided by the area of the steel plate gives the value of the ultimate bearing capacity of soil. Typical load settlement curve obtained from plate load test is presented in the slides. One can refer to the specification and interpret the result and get the ultimate bearing capacity of soil. We will not go into detail about it. We will emphasize the theoretical methods, among which Terzaghi bearing capacity theory is our focus. In 1943, Terzaghi derived the bearing capacity equations based on pronto failure mechanisms for footing at the depth of dF below the ground level of a homogeneous soil. For most shallow footings, the depth dF, called the embedment depth, counts for frost action, freezing, thawing, and other environment effects. In his theory, Terzaghi made the following assumptions. 1. The foundation is strip, that is, length to width ratio greater than 5. 2. The base of the foundation is rough. 3. The soil above the foundation base is simplified as uniform distributed load. Q equals to gamma times dF. The failure mechanism assumed by Terzaghi for determining the ultimate soil bearing capacity for a rough strip footing located at the depth of dF measured from the ground surface is shown in the figure. Terzaghi divided the shear failure area into three zones. The soil wedge below the footing is zone 1, ABJ, which is an elastic zone. Zones marked 2, AJE and BJD, are the radial shear zones, and zones marked 3 are the Rankine passive zones. The rupture lines JD and JE are arcs of a logarithmic spiral, and DF and EG are straight lines. Consider equilibrium condition of wedge ABJ. The force acting on ABJ are W, weight of soil wedge, C, cohesive force acting along each face, PP, the passive force acting on AJ and BJ, faces of soil wedge. Consider unit length of the footing. The ultimate bearing capacity QU can be expressed as equation 1. Terzaghi pointed out that the passive pressure PP in equation 1 is the sum of the contribution of weight of soil gamma, cohesion C, and the surcharge Q. And finally, he proposed the following equation for determining the bearing capacity of soil, which is expressed as equation 2. It is referred to as the Terzaghi bearing capacity equation. In this equation, C is the cohesion of soil, gamma is the unit weight of soil, and Q equals gamma times dF. The terms of NC, NQ, and N-gamma are called the bearing capacity factors. The terms NC, NQ, and N-gamma are defined by equation 3 to 5. and the variations of bearing capacity factors are given in the table shown in the slides. You should keep in mind that the equation 2 is only suitable for strip footing. If it is not the strip footing, you need to take into account the shape factor. For square and circular footing, Terzaghi also provides bearing capacity equations, as shown in the slides. Terzaghi's bearing capacity equations have now been modified to take into account the effects of foundation shape, depth of embedment, and the load inclination. In this slide, it provides the general bearing capacity equation that considers those influences factors. Many design engineers, however, still use Terzaghi equation, which provides fairly good results considering the uncertainty of soil conditions at various sites. This is all for today. Thanks for your attention. See you next time.